Okay, so hello everyone. Well, in this video, I wanted to explain or to make some exercise related to induction motors. Well, remember that, the induction motor can be modeled from an electrical point of view between two circuits. We have the stator circuit model and the rotor circuit model. But instead of working with two circuits at the same time or analyze two circuits at the same time, what you can do is to refer the circuit to the stator, and you can obtain the following equivalent circuit for the induction motor, in which we have R1, that is the resistance of the stator, X1, that is the impedance of the stator. Also, we have these two, this resistor and this impedance in parallel. RC is the resistance of the core, okay? And Xm is the magnetic reactance of the core of the stator. The reason of using these two electrical parameters is to consider the effect of the core in the electrical behavior of the induction motor. Physically, these two elements do not exist, but at the end, we can use these elements in order to model or consider the effect of the core in the electrical behavior of the machine. Also, we have here the impedance of the rotor that is labeled as X2, and also we have the resistance of the rotor that is R2. And I'll notice that the resistance of the rotor is also dependent on the slip of the motor. So this is also important to know because if you increase the slip, well, you can have a lower resistance. If you reduce the slip, well, you will have um, a greater resistance. Okay. So also notice that, well, here the voltage, here is the phase voltage. This means that here we are modeling only one of the three phases of the induction motor, but we can use this model and only multiply the results by 3 in order to consider the effect of the three phases of the induction motor. The reason also that we are introducing this equivalent circuit is that, well, we can also compute the power flow and the losses of the induction motor by using the following diagram. And notice here that here we have the input power that is basically computing the square root of the line voltage times the line current times the cosine of theta. And this cosine of theta is the power factor of the motor. And also, we can compute the stator copper loss by considering the resistance R1 and also the current I1. Okay, that this is basically the current that is flowing in this branch, I1. And I2 is the current that is flowing through the rotor circuit. And well, you can also use this I2 and R2 to compute the air gap power. Moreover, you can compute the rotor copper loss in the following way by considering I2 and R2. Okay, this is the equation for the rotor copper loss. And also you can compute the converted power by using the electrical parameters of the induction motor. You can consider the current I2 and the resistance R2. And based on this, you can compute the converted power. But also, if you have the air gap power, you can take the air gap power and multiply this by 1 minus S. And this is another way to compute the converted power. But you can use this electrical relationship to compute first the air gap power and then the converted power. And well, also you can use this diagram to compute the output power of the motor by considering the mechanical losses that are placed in this section. So based on this diagram and the previous circuit, well, we can use this information in order to solve the following exercise. And in this case, we have the following information. We have a 460 volts, 25 horsepower, 60 hertz, 4-pole star connected induction motor that has the following impedances in ohms per phase referred to the stator circuit. So based on this data, we know that the resistance and the impedances that are given to us are basically referring to the impedances and resistance of the equivalent circuit of the induction motor, both refer to the stator. Also, they are telling us that the total rotational losses are 1,100 watts and are assumed to be constant. Also notice that the core losses is lumped with the rotational losses, and also the slip of the motor is 2.2%. So based on this data, we need to compute the speed of the motor. Okay, we need to compute the speed. Also, we need to compute the stator current. Okay, and we need to compute the power factor and the converted and the output power. Here we have the converted power, and also we need to compute the output power. And also we need to compute the induced torque. Okay, that is another point. The induced torque and the uh, load torque. Okay, remember that the load torque is like the final output torque that the machine is providing. And also we need to compute the efficiency. Okay, and the efficiency is essentially taking the output power and divided by the input power. And so, well, based on this data, we can solve the problem. So let me stop sharing my screen and let me go back um, to I will share my tablet in order to explain to you these points. So let me go to my tablet in just 1 second. Okay. Okay. Just 1 second, just 1 second. Okay. So this is my tablet. In fact, you can see here that I already draw the circuit by the stator or sorry, the circuit of the induction motor, but refer to the stator. I have drawn the original model. Also, notice that I only replace the values that we have. This is the value of R1. No, I put it here. This is X1. This is R2. This is, well, no, this is X2. This is R2. And this is divided by the slip of the motor. That, remember, that was of 2%. So I remove the 2% and divide this in this part. This is the XM, that is the magnetic reactance. Also remember that this is an imaginary number. And well, remember that we are working here with a star connected motor. So we know that for a star connected induction motor, we know that the line voltage is equal to the square root of the square root of 3 times the phase voltage. So based on this relationship, we can compute the phase voltage, and we will have the line voltage divided by the square root of 3 is equal to the phase voltage. Okay. So based on this information, we need to compute the speed of the motor, the stator current, the power factor, the converted power, the output power, the induced torque, the load torque, and also the efficiency. So what we can do first is to compute the speed. So the speed is basically the speed of the rotor. So we have the following formula that is telling us that the slip of the motor in percentage is equal to the synchronous speed minus the rotor speed divided by the synchronous speed. And we can compute the synchronous speed of the motor by using the following formula. No, we have that 120 times the frequency of the supply voltage divided by the number of volts. So we know that, well, this is equivalent to 120. The frequency of the motor is 60 Hertz based on the data given by the problem, and the number of poles is equal to 4. So the synchronous speed is equal to 1,800 revolutions per minute. Okay? Now, we can substitute this value into this expression. Also, I was forgetting to place here 100. Now we are multiplying all this expression by 100 because we are working with a percentage. Also, we know the value of the sleep, that is 2.2%. This is the synchronous speed, that it is 1,800 revolutions per minute, minus the rotor speed, and you need to divide that by the synchronous speed. That is, well, is the same value that we have. Okay, so this is 1,800 revolutions per minute. Well, we can solve these equations for the rotor speed, and you will obtain the following. This is equal to 1,760 revolutions per minute. Okay, so you can use this equation to compute the rotor speed. And well, I think that's it. Now, this is the speed of the rotor. That is the speed of the motor, okay? And well, also we need to compute the stator current. So I will be working with this circuit again, and we need to compute the stator current. Okay, how can we compute that? Well, we know, or we can compute the phase voltage, okay? Because we know the line voltage. In fact, we can say that the line voltage, based on the data given by the problem, is equal to 460 volts divided by the square root of 3. So what you can do in order to know what is the current that one of the phases of the circuit is demanding is to first, well, perform the following. We can simplify the circuit, okay? We can simplify the circuit in order to, first. Okay, so let's just simplify the circuit. If you simplify the circuit, you will obtain the following. Okay, first, I will be adding together the resistance of this term and the impedance of this term. Okay, so, well, we can compute that as, well, here is the resistance, that is 0.6141 ohms. Okay, this is the impedance, that is J point, J times 1.106 ohms. And well, here we have the magnetic reactance, that is 26.3 ohms times J. And if we simplify this resistance, okay, of the rotor plus the impedance here, you will obtain the following. You will get 15.09, okay, 0909 plus 4.464 J ohms, okay? Remember that here we have the phase voltage, that is 460 volts divided by the square root of 3. Now we can simplify this further because these two elements are in parallel, okay? So if you simplify these two elements that are in parallel, you will get the following. Just let me 1 second. That is 15 points plus 0. Okay, just 1 second. I am computing the value. Okay. So, well, if you simplify these two elements that are in parallel, you will get the following. Okay, you will have here your resistance. And well, if you express the equivalent impedance of these two, you will get 12.9217 with an angle of 31.19, 20, 13 degrees. Okay, and these are ohms. And well, you can simplify this further. You can add together these two impedances and you will get the following. Remember that here we have the phase voltage. That is, well, if you compute the equivalent impedance of these three elements, you will get 11.6962 plus 7.79 and 63 J ohms. Okay. And well, we have simplified the circuit. Based on this, we can compute the current, okay, that the phase is demanding. Okay. And remember that, well, this current is essentially the current I1. Okay. So I1 can be computed as this voltage, that is 460 divided by the square root of 3. And we need to divide that by the impedance. No, that is this value, that is 11.6968 plus 7.79, 63 J ohms. Okay, so this is I1. And what else? Well, if you compute this expression, you will get the following current for I1, that is 18.89, 30 with an angle of minus 33.68 degrees. Okay, so you can compute I1, okay, that is the current that is being demanded by the phase of the induction motor. Also remember that for a star-connected induction motor, the phase current, that in this case is I1, is equal to the line current, okay? And also, well, we can compute the power factor of the motor. No, that's one of the points that we need to compute. No, the power factor. We have computing the current of the stator. Okay, because we know that, well, this is the phase current. The phase current is equal to the line current, and this is the value that you need to get. So this is the second point. But also, we can compute the power factor. Remember that the power factor is equal to the cosine of the phase angle of the voltage, that in this case is 0, minus the phase angle of the current, that is minus 33.68 degrees. Okay? And, well, if you compute this power factor, you will get the following, that is 0.832. And, well, based on this data, we can also, well, there is a way in which we can determine if the power factor is leading or is lagging. And the easy way is to see that, well, in the induction motor, we have only inductors. So since we have a purely inductive load, we can say that the power factor is lagging, okay, because we only have inductors in our circuit. But another way to know that, well, this power factor is lagging is to take the phase angle of the voltage, that is 0 degrees, and this is the phase angle of the current, that is minus 33.68 degrees, and this is the current. And if we analyze this this diagram, well, this reference from this point of view, you can see that the voltage is leaving the current. So since the voltage is leaving the current, we can conclude that the power factor is lagging, okay? Because the current is lagging the voltage. Okay, now, this other point that we needed to compute is to compute the converted power and the output power. So to do that, well, we need to compute, well, use the power flow diagram, okay? So the first thing that we can compute is the input power. The input power is equal to the square root of the line voltage times the line current times the power factor. Okay, I will put it in this way. No? And well, we can compute these as follows. We have the square root of 3 multiply by the line voltage, that is 460 volts, times the line current, that is 18.89 2930 times the power factor, that is 0.83 to 1. Okay, so we can compute the input power as 12 525.504 watts. Okay, this is the input power. And well, we can also, with this input power, compute the air gap power. We know that the air gap power is equal to the input power minus the power losses, the stator copper loss, minus the core losses. Okay, but in this case, we can neglect the core losses because the core losses are lumped together with the rotational losses. So we can compute the air gap power as the input power minus the stator copper loss. So we have the input power minus the power, the stator copper loss. We can represent the stator copper loss as 3 times I1 squared times R1. And well, what you can do to compute this this value, well, we know the value of I1. I1 is, well, we need to take the amplitude here. That is 18.89. Okay. You substitute here 18.89. And also you substitute here R1 and you will get the following. Well, I will write all of this, no? We know that this is 12. Well, this is 12,525.504 watts minus 3 times the magnitude of I1, that is 18.89. And this is square times the resistor R1, that is 0.641. And well, the air gap power is equal to 11,840.169 watts. Okay, this is the air gap power. And also, well, we can compute the converted power. And the converted power can be computed as the air gap power minus, well, sorry, we can use a better formula for this. Remember that we have the following relationship, that the converted power is equal to the air gap power times 1 minus S. And this is equal to 11,579.685 watts. Okay, so this is the converted power. And with this converted power, we can compute the output power. and the output power is equal to, um, well, this is the converted power. We can, well, the output power is the converted power minus the rotational losses that according to the problem is 1000 minus, well, 1100 watts. Okay, so well, if we subtract this value to the converted power, you will get 10,479.685 watts. Okay, so this is the output power. And what else we can do? Okay, well, we can compute also the induced torque. Okay, if we know the converted power and we divide that by the speed of the rotor. Okay, so, well, you can get the converted power and also the speed of the motor, but just take into account that this needs to be expressed in radians over second. So we can get this converted power that is 11,579.68 watts, and you need to divide this by the rotational power that is well, sorry, the speed of the rotor, sorry, and we can compute the speed of the rotor because we know the, well, we use this expression not to compute the speed of the rotor. We need to convert this value into radians over second. So you will get 1,760. These are revolutions per minute. But to convert this into radians, you need to multiply this by 2 pi and divide that by 60 in order to convert the value to radians over second. And you will get the following induced torque. That is 500, no, 56, sorry, 0.86 newtons times meter. And then you can compute the load torque that is equal to the output power, okay, divided by the speed of the rotor. And, well, this is equal to, well, we know the output power, that is 10,479.68 watts divided by the rotor speed, that is 1,760 times 2 pi divided by 60. And this is equal to, just one moment. Sorry, I make an error here. This is not the induced torque. I got confused. The induced torque, no, if you compute all of this, is equal to 62.8283 newtons times meter. And below we have 56.86 Newton times meter. Okay. And based on this, we can compute the efficiency. Okay, because we know the output power. Okay. And we also know the input power. And we can multiply this by 100. And you will get the following result, that is 83.66%. Okay, this is efficiency. And, well, you can see that it's a very long problem because you need to complete all of this. But this is a way to solve the problem. Okay, it's not too difficult. The important factor here is that you need to follow the power flow diagram that we discussed previously. Okay, so what I recommend to you is that you need to take into account this power flow diagram. Now let me go back a little bit and let me show you the power flow diagram. Let me go to this presentation. Okay, this is the power flow diagram. in this slide. Okay, so you only need to take into account this power flow diagram in order to compute the what we need at the end is the output power, and that's it. So I hope you like this video. I know that this was a very quick explanation related to this problem, and in the following video, I will explain also how you can compute the maximum torque and the maximum slip that you can produce with an induction motor based on the electrical parameters. So see you next time. Los veo.